So I'm going to do like a sign in or whatever you call it on Friday and Monday. Hopefully we can get everybody on.
I have to be in Cleveland for a mandatory housing tour for my work, so I will not be there.
All right, that's okay. I mean, I'll still have it on Zoom, but I'll just take attendance. So don't worry about it. For your job or something?
Yeah.
Okay. Good. Cleveland. No. All right. Let's see. So what is the number 3? Oops, that's not it. Actually, yeah, this is going. That's so yeah, this is the okay. We got the Zoom running. I guess I should go through this. I think everyone did okay on it. I mean, people didn't turn it in. A few people like they were late. I haven't corrected those yet. Maybe I've already gone through this stuff. The distribution thing, all right. The groups didn't. Oh, sorry, I forgot that. So yeah, I mean, I wanted you guys to plot. So most of the groups plotted it, but sketched it by hand or something. So it'd be good if you knew how to plot things. I mean, so anyway, it'd be good if you can take a function and plot it to compare the different functions. That's the idea on a real graphic thing. So that was the only problem with that. They'll have 2 parameters because they're not. So if they're not normalized, they'd have 3. Like the amplitude would be 1 parameter, but because they're normalized, the integral of it's 1, so the amplitude's fixed.
What sort of data were you expecting us to plot?
Take a sigma and a mean and like do the same thing for the 3 functions. Like a mean value and a sigma, and then just plug it into the function and get it to kind of work. The other thing is that people had a different version of the, like he gives the, is this the right paper? Yeah, he gives the, this distribution function, right? So it's got 2 parameters, like the mean and this z parameter, and he says how the z is related to the polydispersity, which I guess is something like the standard deviation. But it's the square of the standard deviation is a variance, right? So it would be like the variance. Anyway, so it's 2 parameter. It's normalized, so it would have an amplitude if it was not normalized. To normalize it, you integrate and set that integral to 1. So then you divide by the integral of it. So that means you lose the amplitude part. So I don't know. All right. The problem with this function, I guess no one got that, but that function was derived by Flory and Schultz for polymerization of, free radical polymerization, right, for a specific task. And task, so it isn't appropriate really to use that distribution for something like the radius of spheres. I mean, it might work, but basically the other things actually mean something, like the log normal and the Gaussian are functions that have some meaning for spheres, and this thing has a meaning for polymer chains, length of polymer chains, molecular weight distribution. in that sense, it doesn't make any logic to use this Schultz thing in this case, you know. The nice thing about the Schultz is that all three of those are, you can integrate them to get the means. So you can get an analytic function for the mean, each of the moments of it. It's like the weight average molecular weight is a specific answer to it, like a math equation. So, and that's true of the Gauss too. So that's why, and it, like if you just came up with some distribution off the top of your head, it wouldn't have an analytic integral. You'd have to do numerical integration to get the means. Right? You take the value times the distribution would give you the whatever moment you want. Like the first moment would be the value times the integral of the value times the distribution. So second moment's the one people want, which would be the standard deviation. So anyway, so distributions are kind of useful. It's good to kind of play around with them a little bit. And then any questions on that? I don't know. Anyway, mostly people just got that. Okay, I took a couple points off. We didn't know how to plot in a plotting package. Then the double sum, I already kind of went through that, I think. This thing got pretty confusing. Like you have to kind of read the paper. So people lost points in C because they didn't figure out what he was saying here. And it's confusing to me too. So basically, he's got the three, the SM is the one that matches. SM's like the experimental because he's instead of taking the separate form factors, he takes the average form factor. So when he does the experimental, he does exactly that. He does a measurement in the dilute condition where this S of Q is 1. Then you can get this average form factor. And then you take the measured intensity at concentration, divide by that thing. So that's what he's doing in this calculation. Divide by the average, so the dilute one, take the measurement, divide by the dilute, and then you get this, the S of Q part of this thing, which he calls SM. So then the other way to do it, there's two other ways. One, you say it's monodisperse. I guess that's measure for the, one's monodisperse and one's the actual one that he did, like the actual this thing. Right, so I think that's the three, the way I remember it. And then the experimental one matches with the one that's calculated the way that you do the experimental. And then he doesn't monodisperse, he does that calculating with the full different sphere sizes from the distribution function. So those two don't work. The one he does like the experimental works. And this is probably the process of, or it's like when he wrote this, or him or her, who was this? Joel, so him, when he wrote this thing, this is probably his process of, like he started out with this complicated thing and he realized it didn't match the data. Why is that? Well, it's because he's doing this thing, whatever that is, the second one, the one with the mean. And then this one. And then that showed that it worked. And once he did that, he realized, well, wonder what it looked like if it was monodispersed, and he found out that didn't look good. And it's kind of not any information on that, except that he probably went through that process and he just did it. So he just showed it. I showed how that worked. Anyway, it's kind of interesting trip down whatever thing he did. And so this thing, so some people got that just right, and then some people messed this thing up, like just the calculation of end-to-end distance. If you're given some information, like you're given the persistence length, so the Kuhn length is twice that. He gives the contour length, so the contour length divided by the Kuhn length would be the number. Most people got that. Some people muffed it up, you know. And then once you have the number and the Kuhn length, then you can calculate the size of a Gaussian chain and the size of a expanded coil. And anyway, the sizes don't match up. That leads to some problems. So I think, except for mathematical and kind of not getting the numbers right, everyone kind of was on track a little bit on that.
Being smaller.
Yeah. I mean, I gave it in class. I think it ends up being like 11 angstrom, 11 nanometer for the expanded coil one, and 7 nanometer for the Gaussian one, and it should be the Gaussian one. So, and he gets 35 nanometers. So it's like a factor of 5 or something different. So it doesn't match up. Not with the, he never makes a cartoon of what the thing is either. So you don't know exactly what his model is. So he doesn't actually commit to anything. So, but the idea that the extended length would explain that doesn't make any sense at all. Like that the chains are like a brush conformation on the surface, given that the PDMS is insoluble in the solvent. It's not really possible. So, and then this basically anything went, as long as you said something about it. And some people got extra points on this because they went through 3 pages of discussing this topic. So I gave them some points for that. One group did, but other people gave a paragraph or even a couple sentences. So that's about it for that thing. I mean, I already went through it a couple times, so you can vary that. Any questions on this thing? All right, so everyone's here. Some people are here. So anyway, on Friday, Yavit's coming in, at least for part of the class. So everybody has to show up. So I'm going to do an attendance sheet, and then on Monday, John Nichols is going to come in to talk. And then Yavit's talking about dynamic X-ray scattering, and Yavit will talk about. Yavit will talk about dynamic X-ray, and Nichols will talk about quasi-elastic neutron scattering, which is they're both have done that. Nichols has done a lot more quasi-elastic neutron than Yavit's done quasi-elastic X-ray, but X-ray is a newer technique too. So anyway, yeah.
I have a question about Monday. I was gonna email you, but my family's going out of town to watch the eclipse.
Oh yeah. Oh shoot, I forgot about the eclipse. Oh yeah, that's not gonna work on Monday.
Because I'm gonna.
I forgot all about it. Yeah, no, that's all right. All right, Monday is not gonna work. All right, forget about Monday.
Okay.
Yeah, I'll just do like a Zoom class on Monday. Yeah, I forgot all about the eclipse. What?
I said I can join it.
Oh, okay. Yeah, I might not even do it live. I might do a recorded one or something. I do it earlier in the day or something like that. I haven't really.
Supposed to be at.
3. Yeah.
Okay.
So, yeah, no, I forgot about the eclipse. Yeah, that puts a monkey wrench in the whole thing. But thanks for reminding me. All right, so yeah, because I just emailed them this morning. So it's like, all right, so Friday will work. Monday won't work. So maybe I'll either dump Nichols or we'll do it on Wednesday or something. Sorry about that. I totally forgot about Monday. All right, so
How do you spell the first guy's name?
Yavitt, and Ben is his first name. Yeah, so that's probably, he's pretty down to earth. So I think there'll be like Nichols is a little bit higher. So things can get confused, like because he's already at this high level and it's like, so, but yeah, it's like definitely down to earth. I think I never actually heard him give a talk. But I think he's down to earth, that it would work out pretty good. So maybe that'll be good. All right, so Friday we'll have him. And he said like 10:30, so I might do something like go through the problem thing for 20 minutes until he shows up, something like that. And then it might be his paper, so, and then anyway, so it'll work out somehow, but everyone has to show up on Friday. That's the thing. Everyone is like, doesn't have some weird excuse or whatever. So not that the excuse is weird, but all right. So anyway, so I went through last time. All right, so these are old slides. They're in the old format, this clear thing. So I think I went through all of this business about the hydrodynamic radius, about the intrinsic viscosity to the point of I don't really want to say much more. There is a historical context. This guy, Simha at Case Western, he was like so they have a Polymer Science department. And then he was like, kind of like the grandfather of it, as far as I know. Like I met him once, a long time ago. I think he's dead now, but anyway, he lived to really old, like 90, something in his 90s, you know. Anyway, so anyway, he's one of the fathers kind of this is a biography of him. But one of the things he did, I think the main thing he did, as far as I'm concerned, is this intrinsic viscosity thing with biomolecules. Oh, yeah, so he is dead. He's dead in 2008. So, but talks about what he was a European scientist, and then he went to New York. So Columbia had a few people that were big in polymers, but then he moved around, right? So his first work though was working with Hermann Mark when he was at Vienna. So Hermann Mark ended up Brooklyn Polytech, right? And he's the one that did the Mark Holenk equation. The intrinsic viscosity was K times molecular weight to the power. So the Mark Holenk coefficients, like his thing. And he also was kind of he was dead before my time, but basically one of the fathers of American polymer science, but from Vienna. And then this Einstein equation, the solvent viscosity times 1 plus 2.5 times the volume fraction gives you the solution viscosity. So 2.5 divided by densities, the intrinsic viscosity for solid objects, like 3D objects. So Guth took that equation and put it into talk about composites. Like, so you say that the composite modulus is the polymer modulus times 1 plus 2.5 times the volume fraction of filler in it, plus 14.1 times the volume fraction of filler squared. That's called the Guth-Gold equation. We're talking about composites, right? So anyway, so Guth, so this Simha, I guess, worked with Guth and Mark in Austria, and then he developed this business of. So his project is, I think his PhD project was like to figure out how to do this for different shaped things like spheres, and then Einstein had 2.5 for spheres, and then like nu would be 2.5, and then find out what nu is for different things. And this had relevance for like looking at viruses, like biological things, mostly. So this is kind of what he was known for, but he also did this stuff in glass transition with the free volume of glass transition and using positron annihilation to look at the extra space that's in materials, and kind of this packing thing about how to quantitate that packing thing about when you add like 2% extra volume, you get a liquid from a glass, that type of thing. So anyway, this thing gives his whole history. It's kind of interesting. But I didn't realize that he was at Southern California, and then he moved to Cleveland, which is like, it's got to be a down thing. And like, especially in the 50s, like, I think it was pretty nice. And now USC's in the ghetto, like if you go there at night, there's like helicopters flying over with spotlights looking for people, killing people, but so I think it's one of the schools. So did you guys read that there's tuitions that are $95,000 this year coming up, So basically USC is one of those schools. Like it's more than $90,000 to go there. So basically movie stars, kids go there, I think, or something. I don't know. But anyway, somehow was there. So, and then he moved to Case. So they must have given him a ton of money to go from Southern California to Cleveland. I mean, basically, not that Cleveland's bad, but the weather stinks.
Western's also pretty expensive, but they've got some nice things on campus.
Yeah, but USC does too. But I mean, I don't know. It's a lot of money, So once you're done, you owe like at least $500,000, right? I mean, if it's loans, that's going to take you a long time to pay off.
Western's private, so they're.
Yeah. But I don't think it's that high, is it? I don't think it's 90. I think with the help they give you, it's kind of similar. But I don't know. But it's a smaller school too. I mean, it's only got like 10,000-15,000 students, right? I think so. It's kind of a different environment. Anyway, so anyway, it gives his life story. It's all. That's what's here. So anyway, so that's the only thing about the intrinsic viscosity I didn't mention, but so we got that business. So it's a simple measurement. Another simple measurement is this is all about branching. So maybe I'll just skip that for now, but basically branching, so you get a different dependence on molecular weight, basically because the fractal dimension of the thing's different, right? So, and as you go up, the density of the chain changes with mass for higher fractal dimension. So that leads to deviations from this intrinsic viscosity being linear. Log, it's following the Markovnik equation, be a straight line here. Like log would be a power law dependence. Then same with polyelectrolytes I mentioned, like as a chain charge. So as you add more chains, as the concentration increases, you get a drastic change in this value because it goes from being a rod, polyelectrolytes like a rod usually, and then once you Debye screening from the counter ions makes it into like a normal polymer, then the intrinsic viscosity drops because it goes from a rod to like a coil. So you have this transition, which you can map out in terms of like a concentration effect where you go to coils in a polyelectrolyte. Right, so people have looked at this. This Colby guy at Penn State's one of the main ones doing this now. Before that, basically a lot of the intrinsic viscosity stuff was Simha and his people, that case. Right? So anyway, so there's another, so it's a really simple technique to get molecular scale features, right? Information, if you want to analyze it. So the other simple technique is this dynamic light scattering measurement. So I don't know if I have a picture of a machine here. It's not. So let me see if I can find one. It's a good place. So it's about a $10,000 equipment fee thing. They must have a picture of it. Nope. Okay. Flips. I want to see a picture of it. So these things are kind of like, there's a picture here. So you can't exactly see what's going on inside of it, but oh, this is for sale, right? So basically there's a laser. Yeah, there's got to be a picture that shows inside. Images. This is the thing I have. This is kind of a sketch. There's one of these down in the characterization center in the whatever research center. Anyway, this is the idea. So it's simple. Like you have a laser. It doesn't even really have to be. You don't need slits or anything. Like you can just shoot the laser in. I mean, it has slits, but you don't need them. And then basically you pick up at some angle, right? So you're gonna, and what you see is that because the laser's coherent, so all the waves in a laser have a peak at the same time, right? So that's a coherent. So if light isn't coherent, the waves kind of interfere with each other, and then it doesn't travel as far because light can only travel so far before it destroys itself, because the waves aren't like from a light bulb. So a light bulb, you have the light, but if you're a mile away, you can't see it basically. But a laser, you can see it forever basically. That's why it traces across the room, because it's coherent. So anyway, so sunlight is coherent too, because the light comes from the sun, and by the time it reaches the earth, all the things that were out of phase have destroyed each other already, because it's a zillion miles away, right? So basically, it's also collimated and coherent. Collimated means the beams are all parallel to each other. So opposite of focused, right? So the beams are or divergent would be opposite of focused, but collimated is in between focused and divergent beam, right? So you have collimated, monochromatic, there's a single kind of event, energy event going on. These are just one wavelength, and then coherent means they're all of them are in phase with each other. And so that's kind of the three things you need to do this. And then once you shoot something like that into a liquid, you get this speckle pattern thing going on, which is in here too somewhere. There's definitely a picture of it in here. Let's keep on. I think it's just a link to the speckle pattern. Video of a speckle pattern. So this is what you see. The things are like flickering, kind of. So this is just a laser going through like milk, right? And then when you see it, when you look at it, oops, it's got that flickering thing. Just going to redo it. So the flickering particles like moving in and out of the beam, basically. Particles are like they're moving towards you, away from you, but they're basically moving in and out of the beam. So every time they move in, it gets bright, and when they move out, it gets dark. So the flickering has to do with the transport.
This is the reason why I've canceled my.
Anyway, so that's the idea here. You're gonna look at that flickering. When you look at the flickering, what does this guy do? I've lost my thing because I didn't do that right. Not that one. Yeah. Okay, so when you look at that flickering, if you look at it as a function of time, it's going to look like have it here somewhere. Well, basically look like something like this. Right, so you have the light at one point, so one Q angle, right? So Q, 2 pi over Q defines a size scale. So you have kind of a parameter distance R that you're looking at. So you have, in order to get a beam of light coming out, there has to be whatever the colloid is, like a bead at one point and a bead at the other point. So that, and they're going to move, so that means that they can generate a, if they're aligned right, they can generate a scattering event at some point, right? So Q is going to define the distance over which you're looking at the particles, right? And then the flickering of it is going to look like this. So it's flickering at some size scales. This is time and Q. It's like both two parameters to this, the time dependence and the Q dependence. The Q dependence is giving you a size. The time dependence is giving you this flickering thing, which has something to do with the motion, right? So that thing basically, what you do with this noise pattern is you do a correlation function. So you're going to take a point here and then a point some time distance delta t away, right? And you're going to say, what's the probability of finding the same intensity at those 2 points? Right, and then, so if you're close, that probability is really high. And if you're far away, that probability goes to the concentration, basically, of the stuff. Right, now there's some probability at far away, but it's just the average probability over the whole thing. But so you have a decaying function. It's going to decay from 100% to something smaller. Right, so that's a correlation function. So basically that's this G2 of time, the intensity at time, whatever, some time, and then at some time with a delta t, this t, which is going to be the argumentary correlation function. And then you're going to integrate that over all kind of starting points. Right? And then you're going to change t to get this function, which will be a decay function. So basically, this thing's going to be this kind of long-term average number you'd get at long times, which is b. That's going to be this other function, the correlation function, which is a deviation from the average. Right. So there's this odd nomenclature they use. They have like G2 is the thing you measure, and then G1 is the thing you want to get, because G1 is just going to be an exponential decay. Right. And because you're looking at diffusion, then the mean squared displacement is going to be time, is going to be the diffusion coefficient times time. So Q is 1 over size, so the mean squared, 1 over the mean squared displacement times the diffusion coefficient is this time, which is a time that it takes a particle to move the distance 2 pi over Q. That makes sense. So you're looking at two things sitting in space. It's flickering because they're moving in and out. when it goes back on, it means you've traveled from that to that. So you've gone that Q, 1/Q distance. Right, so you have a distance to it, you have a time to it, which is this time. So distance comes from Q and time comes from the flickering. Basically, you get this from the gamma, this exponential decay. And then that defines as relaxation time for material. So you have a relaxation time and you can get the diffusion coefficient from this measurement. Because the relaxation time is going to be the diffusion coefficient. But the argument exponential has to have no units. You have time is the thing that's flickering, and then this has to be 1/time, that's tau, relaxation time. So anyway, so basically it's a kind of a simple thing. The problem is that this, so you have to integrate, so you're doing this integral so you're measuring it, you get the flickering. And then as you're getting the measurement, then you have to integrate it. So if you so you could say, well, I'll just collect the data for a month, then just feed it into a computer and then do this integral for a month, right? So your time has to go from 0 to infinity kind of to do this. You're doing that integral. So, all right, so it turns out that computation of that integral for that correlation function takes a really long time. Like the longer you measure, the longer it takes, right? So somebody figured out that you could do that integral with the machine, like with the dynamic light scattering machine, doing this heterodyne thing, which is something that has to do with interference of two waves. So heterodyne means that you like if you say in cable TV, there's 500 channels on the cable, and the way they do that, then it's just one signal. It's just like two lines, like plus minus, right? So basically, how do you get 500 channels into two lines? So each of the TV stations is on a different frequency within that line. And if you have a tuning frequency that interferes with it, so you couple your control frequency with the signal frequency, you can get two signals from that combined signal. One's plus and one's minus. The minus gives you the TV station, and you just tune the frequency of an oscillator against whatever's coming in, and you can tune across all the frequencies that are in the bandwidth of the thing coming in. You can use the same kind of technique with this machine to do this integral, basically. So like a heterodyne analysis of that wave.
You're just decomposing the overall function.
Yeah, you decompose it into different, cosine waves of different time, and you can get that GT real time, and it can do it during the measurement. So versus taking all that data and then doing this, and it literally would take like days to do this. When they first did this, it took them days to take each data set. When you use this heterodyne, so it's all hardware, it isn't software. So it's tuning a matching frequency, right? And then basically you can get the signal out of this instantly. So that made this, and this can be a board in a computer. So that's why the whole thing. So laser is a nice laser, I guess, is like a couple $1,000. Detectors, full multiplier tube, maybe another 1,000. Then this computer board is another 1,000. So it's got like 3,000. You can make your own. Like you can make this yourself, or you can buy it. Most people just buy it, and then the sample is just anything you want to stick into it, right? So basically, you can study commercial materials with this, like milk. Like there's an example of milk here, like this. No, that's an interferometer. It's kind of the same topic. It's within the same topic thing, yeah. But interferometer, you take the two waves, yeah. So you're going to do a Fourier transform, which is going to decompose into sine waves, right? So you're going to have basically it's going to be like a sine wave decomposition. This thing's more. This involves a Laplace transform, which is like this in here somewhere. So it's going to be a sum of exponential minus t divided by tau. So you're gonna kind of decompose it in a different way. So it's similar, like they're in the same subject category, but basically it's a little bit different. Yeah, here's like milk. So you can stick milk into this, skim milk 1%, and because you can get different taus, you can get different radii, each hydrodynamic radius related to a diffusion coefficient. Each of the taus is a diffusion coefficient. We use Stokes-Einstein. get the hydrodynamic radius. So you can get a combination of times and you get this polydispersity curve, like how much versus a hydrodynamic radius, like skim milk, 1% whole milk. This was someone's PhD dissertation. Right? So, and you can do this, it's easy to do. So you can stick essentially anything into it. And you can get data out, it gives you some size. Whether the size means anything is another thing. So it's a popular item industrially. You know, so it's kind of a little scientific, but basically it can give you a size like on a nanoscale using light. So you don't need a TEM, you don't need any special technique to get it. So that's kind of what the dynamic light scattering is. What I do usually is say like, so you're getting this correlation function in time, right? So there's a lot of correlation functions. So this is from the Polymer processing book, which is on, I think I gave you the link to it. All right, so he's talking about correlation functions, but in terms of like extruded baggies or something. Like you put pigment into a baggie, you extrude it, make a film, then you get these streaks. Right. So it turns out like this is at low shear rate, low temperature. So you're getting, want to know how well dispersed is the material. Right. So to get that, you want to say like, instead of time, you're doing position, you say like, I'm at a position here, I'm in a position there. Are they both black or is there white? Right. So if it's both black, then that's good. You know, then so you're going to get a positive response. So if you start at zero length, it's 100%. If you go to distance out, it drops. So this is also a decay function in space instead of time. Right. So you can transform that into some analysis of what's going on. So that's also got to do with the mixing thing. So you get this, what he calls a coefficient of correlation, which is a correlation function. It's the same thing. It's like the 2 points, you vary the distance between them, and then you get this function of R that's a correlation function for the thing, right? So in the processing industry, so then you can get a mean squared displacements of that thing. You can also get a thing called a scale of segregation, which is the integral of the correlation function, gives you size. This is unitless. Integrate dr, you get a size out of it. And that gets larger when you have more separation distance between the streaks and the plastic bag. Right. So it's basically this correlation function approach is how you kind of look at mixing of things too, if you want. I mean, you can use it for a lot of different things, but mixing is one thing where it's useful. This is kind of interesting, but this is also from Tadmor. Basically, so when people get applied, they tend to get things get a lot more fundamental, you know, like in a sense. So you have like, so this is a random distribution of black dots, right? So, and random means that there's a possibility that one black dot can be on top of another one. So there's big black dots and little ones, they're all the same size. It just looks like that because it's random. And this is where you have kind of like excluded volume of the black dots. He's made a 10 dot diameter as an exclusion zone where the dots can't hit each other. Right. So this is kind of what excluded volume would look like. This is with no excluded volume, like the ideal gas law. This is with excluded volume, like the first viral coefficient for a mixture. Right? But he's talking about Polymer processing. Like the ideas are there. It's the same ideas, you know, same stuff basically. So if you do a correlation function on that, you'll get a peak. Like you get some kind of peak out of it. Like this is a correlation function of the baggy stripes, actually from this one of these pictures. And then these are correlation functions for a line perpendicularly spaced stripes, and then over an area of checkerboard. It's like take a checkerboard and just let it go in 2D, like to see. So they both show kind of a linear dependence, and the stripes show different dependence with some kind of preferred, I don't know, distance, cutoff distance here for the correlations. Anyway, so just I think this is from somewhere else, but basically, if your correlation function was a noisy sine wave, so this is a noisy sine wave, and then when you do, this is a noisy sine wave of the distribution, and then you do a correlation function of that, then all of a sudden the sine wave comes out. So this is the purpose of the correlation function. It shows a decay, So it tells you how randomized the system is by the decay. Like whatever X is time or space you have to go before you lose track of the sine wave because it's got noise in it. And then also it shows you like on the early stages, like there's a sine wave here in this thing. So this kind of analysis of noisy patterns lets you pick out features from it. This analysis saying like I go a distance away, is it there or not? Then when you get to long distances, you just reach the mean value, reach a constant value. And the oscillations are because there's a sine wave in this. Like if you go a distance of 5 away, you're likely to find another peak if you start at a peak. Right. So you can't, looking at it, you can't see it. Suddenly it appears when you do this thing. So that's a kind of idea about the correlation function. Anyway, this just goes through the same things. Just showing how you get the G1 number from the G2. You measure the G2. So if it's not normalized, it's GT. That's what actual experimental. Then you take the average over time, take the ratio, get this small g. That allows you to say 1 here. And this G1 is the thing that has this exponential decay, so you get the diffusion coefficient. Then from that, you just get the hydrodynamic from the Stokes-Einstein thing. So this is from this guy, Paul Russo, who's like an expert in this. So he teaches a class just on dynamic light scattering. So basically, these are some slides from it. But in the machine, when you use the machine, it gives you options of how to plot it. So this is an exponential decay. And then when the argument, when time equals tau, then it's e to the -1, which is 1 over e is 0.37. So basically 37% decay of the signal gives you the tau. Or if you do it, if you do a log of time in G2, well, this should be, yeah, G2 because it's got 1 here, right? So then the inflection point of the thing is tau. So like if you do a log time, you can find that 37% from kind of the inflection point. And if you do log linear, it becomes a straight line and the slope is tau. And then if you do log, you get some weird sigmoidal thing. It doesn't tell you anything really, except it compresses the data so you can see it better. The reason that the data gets noisier, so at small times, you're talking about small time differences. So you have a signal like this long in time. Small time differences is a lot of them, right? But a long time differences, like there's only 1 for the full time that you've measured. So the noise, so the error bar gets larger when you go to larger time in this measurement, right? Because basically you have fewer measurements. Once you do the correlation of it, you get fewer numbers to average. So anyway, this is Russo's list of things. For a sphere, hydrodynamic radius is a radius. For a bubble, it's the radius. If it's anything's inside of a sphere, it's the radius. If it's something other than a sphere, it's an equivalent thing that has the same drag coefficient as a sphere of that size. And if you have milk, all bets are off. So basically, if you just stick paint into this, it'll give you a number, but the number might not have any meaning, right? So the measurement is simple to do, but it's fraught with danger if you stick unknown things into it. Like you can stick shampoo into this, and you can get this worm like micelles, and you can get, what you'll get is 2 exponential decays, one on top of the other. So one of them is kind of the lateral motion of the one like micelles, and the other one is like along the one like micelle motion of it. So they're kind of like balloons, like when you have those 2 balloons and you throw them into the air, and they always want to go like a rocket. They don't want to go like sideways. There's a slow motion of the lateral motion. There's a fast motion of the thing flying through like a rocket. Right? So anyway, so you see, if you just looked at the data from that, you'd say there were 2 things in it because it's 2 decays. You'd say it's a bimodal mixture of small things and big things. There's actually just one thing. So analyzing the data relies a little bit on you knowing what it is you're looking at, and then maybe you can figure it out. So this is like the machine downstairs in characterization center spits out. This is what the control of it looks like. It shows you shows you the raw data, and then real time it's showing you this correlation function from it using this heterodyne thing board in the computer. So you can actually watch this thing as it's running. This thing gets better and better statistics at the high end. Like it kind of cleans it up. You can see there's an exponential decay here. This is a can't really read it. This is a log plot, right? So that's why it looks like that. That's the case of. So the log, it compresses the data so you can kind of see, but it doesn't really exactly show you. So this would be cleaner, like you see a straight line. If you did log linear, it's just a button you push on the software to change the plot type. I think somewhere in here, but anyway, it's a simple thing to use, simple machine to use. So anyway, so that was developed in the night, like lasers were developed in the 60s, and then like in the 70s, dynamic light scattering was developed. And then so basically this is kind of like up to like the 80s maybe, and then like now it's just a standard piece of equipment people have. But so there's other things that are going on here. So people do what's called microreology. No one's doing it in our department. Basically, a lot of people are doing this now. So basically, it's based on the same thing as the dynamic light scattering. You get a noise signal, same thing. You're going to do an exponential transform of it, right? So basically, instead of so you have some kind of goo that you have, and you want to know the viscosity of it. So you put beads into it, like either silica beads or polystyrene beads, monodispersed spheres, right? And you put in enough that it looks like milk. So you put a bunch of it in there. They shoot a laser, and you do the dynamic light scattering measurement on that. And you're looking at the beads moving in the fluid, right? So basically, it's a way to get the rheology of the fluid from the random Brownian motions. This is called a passive microrheology measurement. You can also put beads in and say, put them in a field. So you could do an oscillating field, just use like gravity field, like stick a bead into a liquid and then watch the bead fall, and then you can get the viscosity of the liquid from that, right? So, or you can put the bead in magnetic bead and do a magnetic field oscillation and watch it move. So there's different ways. That would be a forced active microrheology.
Each of those beads is made up of a particular polymer.
Yeah, so the bead has nothing to do with it. You're looking at the fluid. The bead is just a way to measure the viscosity of the fluid. It's like the rheometer. So normal rheometer, you're going to have like a cup and bob rheometer, a Couette viscometer, or you can have a cone and plate viscometer. So you're going to basically have the fluid in between and spin it or oscillate it, get the G prime, G double prime from it, right? Or here you just get the viscosity with a cup and bob. So here you're doing something totally different. You're sticking beads in, you're not moving, you don't have any torque, you don't have any strain gauge. There's nothing moving part in this. It's just a laser. You just get this noise out. The thing that's moving is like KT. It's just moving the particles around by Brownian motion, right? So it's pretty simple technique. And then you can detect it this way, or you can, a guy came and gave a talk from Santa Barbara. It would have been a good talk to go to at this point, But basically, you can do photographs of that or like digital images of it, and then do subtraction of the images. And from that, even with a really noisy material, like the subtraction gives you the motion of the particles. And then you can transform that image into all the different Q space, because you're getting the image of the beam scattered. And then do that as a function of time and do the same correlation function to it. So people are like, microrheology is a pretty hot topic in research. We're looking at different systems. The reason why is that one of the reasons why is that you can get. So this is G prime, G double prime. So at low frequency it's a liquid. So this is G double prime with upside down triangles. G prime to circles, and it becomes a solid. That's a rotary plateau right here, and then. So basically, that's the thing you can get. This is worm like my cells. That's what you can get with a normal rheometer, right? So, but you want to see, like, if you want to know about the entire structure of this on the nanoscale, like what is the tube diameter? How is reptation happening? How many entanglements are there? then you need to go to this high frequency where within the tube, it turns back into a liquid. But you can't measure that because if you try to do such a high frequency with a normal rheometer, you get slip at the walls. Like it would be rotating so fast, it would just break. You get melt failure at the walls. So you can only do that measurement up to a certain frequency. That's it. And you can see the noise even starts to come in when you get to high frequency. So, but with this technique, this microrheology, you can easily measure that in. You can actually measure almost the whole thing. So you can see the blue line for microrheology matches up with the experimental rheology, the normal rheology, and it also gives you all this other information about the molecular scale things. Yeah. So it's actually an incredible thing that you can just stick some beads in the thing and then get this out of it. You know, it's like kind of magic. Right? So anyway, so how you do that? Basically, you do the same measurement, and you're going to get. All right, so you get the from the same measurement, you get the, because the mean squared displacement is two times diffusion coefficient times time. So basically tau will give you the mean squared displacement of the particles of these beads moving around. And they're monodispersed beads. So it's just one, there's just one relaxation time to it. So basically the Laplace, so you can, from the mean squared displacement, you get the Laplace transform of the complex modulus. So this is a lot of math. And then the Laplace transforms this thing. So it's a series of exponential decays. And then from this complex, by Laplace transform, so you can measure this directly, mean square displacement. So then you can get this thing as a function of Q. So S is Q here. And then you can Laplace transform this thing into G prime, G double prime, and basically get that curve I showed you. So it's really pretty involved, like how this is done. But this is how you use these techniques to get this modulus, get the complex and storage, the storage and loss modulus. Anyway, so that's that business. So the other things, so there's two other things to say. You can do this dynamic light scattering thing with X-rays from a synchrotron. So like you need to have a big machine that can give you kind of basically coherent and monochromatic X-rays. So you can't do this with a lab source, which is like a light bulb, right? So this is kind of like an X-ray laser in a sense. This is a fairly new synchrotron in New York, Brookhaven, Long Island. So it's about, I think it's like a half a mile diameter, this thing, something like that. So basically this is, anyway, that's kind of what you need to do. So that's what Yavit worked there. So we'll talk about kind of using this kind of dynamic light scattering with X-rays. The other thing with neutrons, so there's two ways to do this dynamic. In the original method to do dynamic light scattering, people used Doppler effect. So you'd have like a monochromatic laser beam comes in, and then because the particles are moving, it broadens the beam out. Because it broadens the beam out, the spectrum of the beam. Like normally you'd have like the intensity versus wavelength, there would be a spike for a laser. And then if you put it through a colloid like milk, that thing broadens out to the left and the right because the particles, some of them are moving towards you, some are moving away. So it's like a train whistle going by. So it changes the frequency, changes the wavelength, and you can get this spectrum effect. So it broadens the spectrum. So the original dynamic light scattering was just measuring the spectrum. So you're just measuring the spectrum from the breadth of it, you get the mean square displacement, and then you get this tau thing from it. So you can get the diffusion coefficient from basically the broadening of the peak. So, and then they figured out you could do this heterodyne business, and that just shut down that whole operation. So original machines were built with these high resolution spectrometers. Anyway, so for neutrons, you rarely can get anything close to monochromatic. Like there's nothing like a laser for neutrons, really. There kind of is. This spallation source is kind of like that. So this is a $500 million instrument. So if you want to see like what $500 million looks like, it's got a linear accelerator, it plows into metal, makes neutrons. They come out time of flight. So if we get Nichols, he'll talk about this thing in some deep, $500 million, right, to do this. And then you can get that kind of broadening. So you can get a measurement of the dynamics from the broadening of the peak, like the original dynamic light scattering machines. So anyway, that's the scheme of, that's called quasi-elastic neutron scattering, which is, it's kind of along the same track as both X-ray and neutron are going to measure much smaller sizes. So you're going to see molecular scale motion here, like transitions that happen in molecules dynamically. So hopefully Nichols can talk about that, maybe not on Monday. So there's some slides from Oak Ridge about that. That's in Oak Ridge, Tennessee, the SNS thing. But so basically they're looking at like frequency and size scale with that, like trying to probe different motions of like biological molecules and things, like in a membrane, like we want to see transport across a membrane or something. Anyway, all right, let's quit there. Yeah, so so Monday, all right, so Friday we'll do the thing with the Abbott. And maybe Wednesday I'll get Nichols to come in, something like that. I can switch a day.
Question. Can you hear me?
Mm.
Hello, can you hear me, Dr. Brown? Yes, he can.
Like the juniors can work together on like a final exam. Are we allowed to ask you questions or like?
Yeah.
I was like worried that it was gonna be like.
Yeah, because you're taking it for grad credit or something. Oh, no, you're a junior.
Yeah. I'm just
Okay.
taking it.
Yeah, no, didn't we say all the juniors would go together in one group or
Yeah.
something? No. Okay,
Which is still fine.
Yeah.
You can still ask questions.
yeah, you can just go in one group.
Yeah.
Yeah,
Okay.
yeah, all right. I think.
Dr. Broush.
Oh, yeah.
Dr. Broush.
They can have like
I just got a new one.